Picture this: a moonlit night, thousands of years ago, where a lone scholar stands atop a windswept hill, eyes fixed on the shimmering tapestry of stars above. No telescopes, no satellites, no advanced instruments, just the human mind, relentless curiosity, and an unshakable determination to unravel the mysteries of the cosmos. This was the world of ancient scholars who dared to ask questions that seemed impossible. How vast is the Earth? How far does the moon hang above us? What invisible forces guide the heavens? These weren't just abstract wonders, they were puzzles waiting to be solved. And with nothing but observation, ingenuity, and sheer brilliance, these thinkers found answers that still leave us in awe today. What's truly astonishing isn't just that they tried, it's that they succeeded. Without the tools we take for granted, they measured the unmeasurable. They calculated the Earth's circumference with nothing but shadows and sticks. They mapped the distances to celestial bodies using geometry and patience. They turned the night sky into a cosmic ruler, and the Earth itself into a laboratory. And here's the thing: their methods weren't just clever guesses. They were so precise that modern scientists, armed with technology those ancients couldn't have dreamed of, often find themselves nodding in respect. How did they do it? That's the story we're about to unravel, a journey back to a time when human curiosity refused to accept limits. This isn't just about numbers or ancient textbooks. It's about something deeper, the timeless drive to understand the world around us. Those scholars didn't have all the answers, but they asked the right questions, and in doing so, they laid the groundwork for everything we know today. From the geometry of Eratosthenes to the star charts of Ptolemy, their legacy is a testament to the power of human imagination. So let's step into their world, where every shadow, every angle, every rising star held a clue. By the end of this journey, you'll see the night sky and the genius of the past in a whole new light. Long before rulers and compasses existed, our ancestors looked to the world around them for answers. The first measurements weren't about numbers, they were about survival. Picture a farmer in ancient Mesopotamia watching the Nile flood year after year, noticing how the water's reach marked the fertile land. Or a shepherd tracking the moon's phases to predict the best time for planting. These weren't just observations, they were the beginnings of a revolutionary idea that nature could be understood, predicted, even quantified. The shift from myth to measurement didn't happen overnight. Early societies saw the sun and stars as gods, their movements dictated by divine whims, but somewhere along the way, curiosity overcame fear. The Babylonians, for instance, didn't just worship the planets, they recorded their paths across the sky with astonishing precision, carving clay tablets that mapped celestial patterns centuries before telescopes existed. Meanwhile, along the Nile, Egyptian priests noticed something remarkable. The star Sirius rose just before the annual flood. That wasn't magic, it was a clock, a calendar, a tool. What's fascinating is how these early thinkers turned everyday objects into instruments of discovery. A simple stick planted in the ground became a sundial, its shadow tracing the sun's journey. Rope knots measured fields after floods receded. Even the human body became a ruler, the length of a forearm, the span of a hand. These weren't crude estimates. They were the foundation of geometry, astronomy, and ultimately, science itself. By the time the Greeks entered the scene, measurement wasn't just practical, it was philosophical. The question was no longer just how far, but how do we know? And that shift from observing to proving would change everything, because when you start measuring the world, you're not just counting, you're asking it to reveal its secrets. Among the giants of ancient scholarship, One name stands out for a feat so bold it still echoes through history: Eratosthenes. This Greek polymath, librarian of Alexandria, didn't just ponder the Earth's size. He measured it with nothing but sunlight, shadows, and a stroke of genius. Picture this: two cities, Syene and Alexandria, separated by hundreds of miles. In Syene, at noon on the summer solstice, the sun shone directly overhead, casting no shadow at the bottom of a deep well. But in Alexandria, a vertical stick planted in the ground still threw a shadow. To most, that might have been a curiosity. To Eratosthenes, it was a revelation. The difference in those shadows told a story. By measuring the angle of the Alexandria shadow about 7 degrees, he realized it represented a fraction of the Earth's full circle. Since he knew the distance between the two cities, he could scale it up. Imagine a pie cut into slices. If 7 degrees is one slice, and the distance between cities is the length of that slice's edge, then the full pie's circumference is just a matter of multiplication. His calculation, roughly 250,000 stadia, or about 25,000 miles, modern measurements put the Earth's circumference at 24,901 miles. He was off by less than 2% without ever leaving Egypt. What's even more remarkable is how elegantly simple his method was. No satellites, no lasers, just the geometry of sunlight and the audacity to trust his own reasoning. He didn't just guess, he proved, and in doing so, he shattered the idea that the Earth's size was unknowable. His work became a beacon for explorers centuries later. When Columbus set sail, he carried Eratosthenes' calculations, though famously ignoring their implications about the vastness of the Atlantic. Even today, his experiment is a masterclass in how observation and logic can unlock the universe's secrets. But Eratosthenes didn't stop there. His curiosity stretched from the Earth's curves to the stars' paths. He mapped the tilt of the Earth's axis, devised the first system of latitude and longitude, and even calculated the distance to the sun and moon, though those figures were less accurate. Yet it's his measurement of the Earth that endures, a testament to a single truth. You don't need advanced tools to ask advanced questions. Sometimes all it takes is a stick, a shadow, and the courage to measure what others thought was immeasurable. The night sky wasn't just a scattering of stars to ancient astronomers. It was a grand, rotating dome, a celestial sphere where every light had its place and purpose. Picture this vast imaginary globe encasing the Earth, with stars fixed like jewels on its inner surface, turning steadily around us each night. This elegant model wasn't mere poetry. It was a practical tool for mapping the heavens with astonishing precision. From Babylon to Greece, scholars plotted constellations, tracked wandering planets, and even predicted eclipses, all by imagining the cosmos as this perfect, measurable sphere. To bring this model to life, they crafted ingenious instruments. The armillary sphere, a nest of metal rings representing celestial circles, let astronomers visualize the sky's motion in 3 dimensions. Then came the Astrolabe, a handheld marvel of brass and mathematics that could measure a star's height, tell time by night, or calculate the sun's path. These weren't just tools, they were portable observatories, compressing the universe's complexity into something a scholar could hold. With them, the ancients didn't just watch the stars, they conversed with them, decoding patterns that repeated season after season, century after century. No one refined this system more than Claudius Ptolemy, whose geocentric model placed Earth at the universe's center with mathematical precision. His Almagest catalogued over 1,000 stars, plotted planetary orbits in intricate epicycles, and became astronomy's Bible for 1,400 years. What's remarkable isn't that he got it wrong, it's how brilliantly his system worked despite that. Ships navigated by it, calendars were set by it, and even when Copernicus later challenged it, Ptolemy's calculations still predicted planetary positions with uncanny accuracy. His legacy wasn't just a map of the heavens, but proof that even flawed models can unlock profound truths when built on meticulous observation. Yet beneath this celestial clockwork lurked a tantalizing mystery. How far away were these lights? Measuring Earth size was one thing, but the stars, they had no shadows to measure, no parallax to detect with naked eyes. Some guessed the moon was mere miles overhead, others thought the stars infinitely distant. The very tools that mapped the sky's movements couldn't bridge that gulf, a limitation that would haunt astronomers until the invention of the telescope. But in their attempts, these scholars did something revolutionary. They turned the immeasurable into a question that could someday be answered. And that shift, from wonder to measurement, was the first step toward touching the stars. While the stars remained stubbornly out of reach for measurement, one brilliant mind turned his gaze closer to home, to our celestial neighbor, the moon. Aristarchus of Samos, a thinker centuries ahead of his time, didn't just wonder about the moon's distance. He devised a way to measure it using nothing but Earth's shadow and the power of geometry. His method was as daring as it was simple. During a lunar eclipse, when the Earth slides between the sun and moon, he noticed something crucial. The curved shadow our planet cast on the lunar surface wasn't just a dark smudge, it was a clue. Here's how his reasoning unfolded. If the sun's rays spread parallel to each other, an insight he'd already proven, then Earth's shadow must taper like a cone. By timing how long the moon took to pass through that shadow and comparing it to the moon's own orbital period, he could estimate the shadow's width relative to the moon's size. Then came the masterstroke. Using the angle at which the shadow's curve appeared, he calculated that the moon was about 60 Earth radii away. That's roughly 240,000 miles, a figure remarkably close to today's measurement of 239,000 miles. What makes Aristarchus' achievement astonishing isn't just the accuracy, it's the sheer audacity of his assumptions. Without telescopes or precise clocks, he trusted geometry to reveal cosmic truths. His calculations hinged on estimating the sun's distance first, which he got wrong, placing it 20 times too close. But here's the twist. Those errors nearly cancelled each other out, leaving his lunar distance impressively close. It's as if the universe conspired to reward his ingenuity. Yet his legacy reaches beyond numbers. Aristarchus was among the first to propose a heliocentric model, imagining Earth orbiting the sun, an idea so radical it was dismissed for centuries. His moon measurement, though, became a cornerstone. Later astronomers like Hypatia refined it, using parallax during solar eclipses to narrow the margin of error. By the time Ptolemy's era arrived, the moon's distance wasn't just guesswork. It was a documented fact proven by shadows and angles. This story reveals a deeper truth about ancient science. Progress wasn't linear. Brilliant ideas often lay dormant until tools caught up with vision. Aristarchus' methods, rough as they were, showed that even the heavens could be measured, not by magic, but by patience, observation, and the unshakable belief that the universe follows rules waiting to be decoded. And that belief, more than any single calculation, would light the way to the stars. The motion of the planets presented ancient astronomers with a celestial riddle that refused to be solved. Unlike the steady march of stars across the night sky, planets like Mars and Jupiter seemed to dance to their own rhythm, sometimes moving forward, then pausing, even reversing course in bewildering loops. To scholars like Hypatia, this wasn't just a curiosity. It was a challenge to the very idea of an orderly universe. His meticulous records of planetary positions revealed patterns that defied simple circular orbits, forcing a radical rethink of how the heavens work. Enter the genius and complexity of epicycles and deference. Picture a cosmic carousel. A planet doesn't just orbit Earth in a perfect circle, the deferent. Instead, it rides along a smaller circle, the epicycle, which itself moves along the larger path. This double motion, painstakingly calculated, explained why planets appeared to slow down, backtrack, or brighten and dim. Ptolemy later refined this system in his Almagest, adding eccentric points and adjusting speeds until the model matched observations with uncanny precision. For over a millennium, this intricate clockwork of circles upon circles was the pinnacle of celestial mechanics, yet the model's brilliance hid a growing problem. Each new astronomical discovery demanded another epicycle or tweak to keep the math aligned with the sky. By the Renaissance, some planetary models required dozens of interlocking circles, a celestial Rube Goldberg machine that strained credulity. Scholars whispered doubts: was nature truly this convoluted, or was there a simpler truth buried beneath the complexity? The answer, of course, was yes, but revealing it would require dismantling an idea that had stood for 1400 years. What's often overlooked is how much these flawed models achieved. Without telescopes or precise clocks, Hypatia and Ptolemy had decoded planetary motion well enough to predict eclipses, guide navigators, and set calendars. Their work wasn't just wrong, it was wrong in the most useful way possible, a testament to human ingenuity bending incomplete data into practical truth. And the tools they relied on: armillary spheres to visualize orbits, astrolabes to measure angles, became the stepping stones for future breakthroughs. The persistence of these models speaks to something deeper than astronomy. The human mind struggled to reconcile observation with belief. For centuries, the idea of Earth-centered orbits felt as undeniable as the ground beneath one's feet. Challenging it meant more than adjusting math, it meant reimagining humanity's place in the cosmos. Yet even as these theories clung on, they quietly paved the way for their own downfall. Every precise measurement, every recorded anomaly, was a clue waiting for someone like Copernicus to connect the dots. The puzzle of planetary motion wasn't just about predicting paths, it was about learning how to see the universe anew. The ingenuity of ancient scholars wasn't confined to abstract theories. It was forged in bronze, carved in stone, and etched into instruments of remarkable precision. Take the water clock or clepsydra, a device so elegant in its simplicity that it measured time by the steady drip of liquid from one vessel to another. In the courts of Egypt and the academies of Greece, these clocks weren't just timers, they were the heartbeat of civilization, regulating everything from legal speeches to nocturnal star observations. The trick lay in their design. A tapered interior ensured the water flowed at a consistent rate, compensating for decreasing pressure as the vessel emptied. Some models even included floating indicators to mark the hours, proving that accuracy didn't require gears or electricity, just a deep understanding of nature's rhythms. Then there were the sundials, transforming sunlight into a cosmic clock face. Far from the crude garden ornaments we imagine today, ancient dials were precision-engineered marvels. The Romans' hemispherium, for instance, curved like a bowl to match the sky's dome, with hour lines calculated for specific latitudes. A skilled observer could read time down to intervals of 15 minutes, no small feat when noon wasn't standardized across regions. But the real stroke of genius came with portable sundials like the Roman diptych, which folded like a book and included adjustable gnomons to adapt to different locations. These weren't just tools, they were the ancient equivalent of smartphones, making celestial navigation personal and portable. For measuring angles, nothing rivaled the quadrant. Picture a quarter circle of wood or brass, etched with degree markings and fitted with a plumb line. By aligning one edge with a star and reading where the line fell, astronomers could pinpoint celestial positions with startling accuracy. The astrolabe, its more sophisticated cousin, combined multiple functions into a single device: a star map, calendar, and calculator all in one. Crafted with exquisite detail, these instruments weren't merely functional. They were works of art, their brass surfaces engraved with intricate scales and zodiac symbols. Holding one was like holding the universe in your hands, a tangible connection between earthly craftsmanship and cosmic order. What's often overlooked is how deeply culture influenced these innovations. In China, the invention of the armillary sphere reflected a philosophy of harmony between heaven and earth, its nested rings mirroring celestial spheres. Islamic scholars, driven by the need to determine prayer times accurately, perfected the astrolabe's design, adding features like adjustable plates for different latitudes. Even the materials told a story. Byzantine sundials used marble for longevity, while Persian quadrants employed lightweight brass for ease of travel. These weren't just technical achievements, they were cultural artifacts shaped by the values and needs of their creators. The true legacy of these instruments lies in their dual nature. They bridged the gap between art and science, beauty and utility. A sundial's graceful curves weren't just aesthetic, they encoded mathematical truths, and astrolabe's engravings weren't mere decoration, they were a visual language for decoding the heavens. In an age before mass production, each device was a testament to the patience and vision of its maker, a reminder that precision isn't just about numbers, but about the human hands and minds that chase them. As these tools spread across trade routes and empires, they carried more than functionality, they carried ideas. The same quadrant that measured a star's height in Baghdad might later guide a ship in Lisbon, its design subtly adapted by each culture it touched. This exchange wasn't just about technology, it was a silent conversation between civilizations, each adding its own chapter to the story of how we measure the world. And in that story lies a timeless lesson. The most enduring innovations aren't just built on metal and math, but on the shared curiosity that unites us across centuries. Geometry wasn't just a branch of mathematics to the ancients, it was the very language of the universe, a tool for translating the chaos of nature into precise, solvable problems. At the heart of this revolution stood Euclid of Alexandria, whose Elements didn't just compile geometric knowledge, it built an unshakable foundation for all future science. Picture a world where abstract lines and angles could suddenly explain the curve of the Earth, the distance to the Moon, or the path of a planet. Euclid's axioms, simple statements like a straight line can be drawn between any 2 points, became the alphabet of this new language, allowing scholars to construct proofs as sturdy as stone temples. His work wasn't theoretical musing, it was a toolkit for measuring reality. Take the problem of calculating heights, like determining the depth of a well or the slope of a pyramid. Before Euclid, solutions relied on rough estimates or folklore. But armed with his principles, a surveyor could use similar triangles, a concept straight from Elements, to find unknown distances with nothing but a shadow and a stick. If a vertical pole 6 feet tall cast a 4-foot shadow, and a pyramid's shadow stretched 200 feet, the math was suddenly clear. The pyramid's height stood 150 feet. This wasn't guesswork, it was inevitability baked into the fabric of space itself. The true power of geometry lay in its universality. Whether in the flooded plains of Mesopotamia or the marble halls of Athens, the same rules applied. When Eratosthenes measured the Earth's circumference, he didn't invent new math, he applied Euclid's theorems about circles and angles. Aristarchus, calculating lunar distances, leaned on geometric proportions. Even the astrolabe, with its brass arcs and dials, was Euclid's geometry made physical, turning celestial movements into tangible measurements. But the most profound shift wasn't just in accuracy, it was in mindset. Geometry transformed observation from passive recording into active interrogation. No longer satisfied with "the moon rises there," scholars began asking how far and how fast. They stopped seeing the sky as a scroll of myths and started treating it as a diagram waiting to be solved. This rigor spilled beyond astronomy. Architects used it to design acoustically perfect theaters, engineers to plan aqueducts that defied gravity's pull, and navigators to chart courses across trackless seas. The legacy of this geometric revolution echoes in every modern map, every satellite orbit, every bridge spanning a river. Euclid's Elements became the second most printed book in history, surpassed only by the Bible, a testament to humanity's hunger for a language that could measure the immeasurable. And while later mathematicians would expand the vocabulary with calculus and algebra, the grammar remained unchanged. For in the end, the universe doesn't whisper its secrets in words or numbers, but in shapes, and geometry taught us how to listen. For civilizations that rose and fell by the rhythms of harvest and flood, time wasn't just a concept, it was life itself. The Egyptians didn't just track days, they built their survival around them. When the Nile's annual floodwaters receded, leaving behind rich black silt, priests noted the event coincided with the heliacal rising of Sirius, the moment the star first reappeared before dawn after months of invisibility. This celestial signal wasn't merely poetic. It marked the new year, dividing time into 3 seasons: inundation, growth, and harvest. Their calendar, etched in temple walls and bureaucratic records, became one of history's first solar reckonings, 365 days split into 12 months of 30 days each, with 5 extra days gifted to the gods. But here's the twist: without leap years, their calendar drifted slowly against the actual solar year, wandering a full day every 4 years. Yet even this imperfection revealed their genius, the Sothic cycle, a 1,461-year period where calendar and stars realigned, became a chronological anchor for dating events across millennia. Half a world away, the Maya wove time into something far grander, a cosmic tapestry where dates weren't just noted but imbued with sacred meaning. Their long count calendar didn't just tally years, it stacked them like layers of a pyramid, combining cycles of 20 days, 360 days, 7,200 days, and beyond. A date might read 9 backtons, 14 catons, 3 tons, placing events within a framework stretching back to mythic origins. This wasn't mere record-keeping. It was a philosophy where time spiraled in repeating patterns, each epoch carrying its own destiny. Priests used these cycles to schedule coronations, plant crops, and even predict eclipses with jaw-dropping accuracy. The Dresden Codex, a surviving Mayan manuscript, contains Venus tables so precise they're off by just 2 hours over 500 years, a feat of naked-eye astronomy that still stuns modern scholars. What unified these systems, despite oceans and cultures between them, was their intimate bond with power. In Babylon, kings justified their rule by aligning coronations with planetary conjunctions. China's emperors maintained monopoly over calendar reforms because whoever controlled time controlled the rhythms of society. Even Rome's political chaos seeped into its calendar. By Julius Caesar's era, the year had drifted so far out of sync that winter festivals fell in autumn. His Julian reform added months and leap days not just for accuracy but to stabilize a fractured empire. Timekeeping wasn't scholarly trivia, it was the glue holding kingdoms together. Yet beneath this precision lurked a tantalizing problem: how to measure time beyond human lifespans. Generations could track annual floods, but what of epochs? The Greeks turned to Olympiads, counting 4-year intervals between games. Chinese astronomers chronicled guest stars, sudden bright points we now know as supernova, marking them as celestial signposts in their annals. But the real breakthrough came from an unexpected source: tree rings and sediment layers. Ancient scholars noticed patterns in nature's own archives. The thickness of a tree's growth rings hinted at wet or dry years, while clay deposits in riverbeds told stories of floods centuries past. These weren't calendars in the traditional sense, but they revealed time's deeper currents, showing how the Earth itself kept its own silent clock. The beauty of these ancient systems lies in their duality. They were both practical and profound, linking the planting of seeds to the motion of stars. A Babylonian farmer consulting a lunar calendar wasn't just checking dates, he was participating in a tradition that saw human life as part of a vast, measurable cosmos. And that's the true legacy of these timekeepers. They didn't just count days, they taught us that time itself could be shaped, studied, and ultimately understood. While most ancient scholars focused on measuring what they could see, the Earth, the Moon, the wandering planets, a handful of visionaries dared to ask a far more radical question: how vast is the universe itself? In the bustling agora of 5th century Athens, Democritus gazed beyond the visible stars and proposed something astonishing: that space had no end. To him, the cosmos wasn't a finite sphere but an endless void, sprinkled not just with stars but with countless other worlds, some thriving with life. This wasn't idle speculation, it was a philosophical leap grounded in his atomic theory. If everything was made of tiny, infinite particles, why wouldn't the universe mirror that infinity? His contemporary Anaxagoras went further, suggesting the stars weren't divine lanterns but distant suns, some perhaps hosting their own civilizations. Imagine the audacity of such ideas in an era when many still believed the sky was a solid dome hammered from celestial bronze, yet not all minds stretched so far. Aristotle, ever the pragmatist, dismissed infinity as a mathematical abstraction, insisting the universe was a nested set of perfect, finite spheres. To him, the idea of endless worlds was not just wrong, it violated the very principles of order and centrality that governed his worldview. This tension between the boundless and the contained wasn't just academic. It reflected a deeper divide in how ancients understood their place in existence. Was humanity at the heart of a carefully crafted cosmos, or an insignificant speck in an unimaginable expanse? What's striking is how these thinkers tested their theories without telescopes or spacecraft. Anaxagoras, for instance, studied meteorites, concluding they were pieces of other worlds, a tangible clue to the cosmos's material unity. Others, like the Stoics, pointed to the Milky Way's faint glow as evidence of distant fires, hinting at a universe far larger than it appeared. Even flawed methods yielded insights. When Aristotle argued the stars must be close because they showed no parallax, no apparent shift when viewed from different angles, he wasn't entirely wrong. The stars were indeed so distant that their parallax remained undetectable until the 19th century. His error was assuming invisibility implied proximity, a reminder that even incorrect assumptions could edge closer to truth. The legacy of these speculations lies not in their accuracy, but in their courage. Democritus' infinite void and Anaxagoras' extraterrestrial suns were dismissed for centuries, only to find vindication in the telescopes of Galileo and the equations of modern cosmology. Their ideas were seeds planted in stony soil, waiting for tools and minds to catch up. And that's the real lesson here. Measuring the universe began not with instruments, but with imagination, the refusal to let the limits of the eye dictate the reach of the mind. In the heart of ancient Alexandria, a beacon of knowledge rose from the Mediterranean shores, the Great Library, a monument not of stone and gold, but of parchment and ink. Imagine a place where the world's wisdom converged under one roof, where scholars from Greece, Egypt, Persia, and beyond gathered to debate, calculate, and dream. Ships docking in Alexandria's harbor weren't just inspected for cargo, they were searched for books. Any scroll found was borrowed, copied, and added to the library's staggering collection, which some estimates suggest held 500,000 volumes at its peak. This wasn't just a repository, it was an intellectual engine fueling discoveries in geometry, astronomy, and medicine. Here, Euclid penned his Elements, Archimedes calculated pi, and Eratosthenes mapped the Earth, all within walking distance of each other, their ideas cross-pollinating in ways that shaped centuries of thought. But Alexandria wasn't alone. Across the ancient world, libraries served as the hard drives of their era, preserving knowledge against the erosion of time. In Nineveh, Ashurbanipal's library hoarded 20,000 clay tablets, including the Epic of Gilgamesh, saved from oblivion by the very fire that destroyed the city, baking the tablets into durable ceramic. Pergamon's library rivaled Alexandria's, pioneering parchment when papyrus embargoes threatened their scroll supply. These institutions weren't passive warehouses. They were alive with activity, scribes translating texts, astronomers comparing star charts, physicians compiling remedies. The library was a workshop where the past informed the present, and the present built the future. The loss of these centers struck like a blow to human progress. When flames consumed Alexandria's library, whether by Julius Caesar's accident, Christian zealots, or later caliphates, countless works vanished forever. Aristarchus' treatises on heliocentrism, Heron's blueprints for steam engines, entire plays by Sophocles and Aeschylus gone. The tragedy wasn't just the destruction of books, but the severing of connections. Imagine how history might have unfolded if Hypatia's mathematical teachings had survived intact, or if the library's full astronomical records had passed to Galileo. The Dark Ages weren't just a lack of light, they were a scattering of embers that could have roared into flame. Yet from this fragile chain of transmission, certain figures emerge like torchbearers in the dark. Think of Ptolemy, whose Almagest survived to guide Copernicus, or Galen, whose medical texts dominated Europe for a millennium. Their endurance hints at a profound truth: knowledge is resilient. Even as libraries burned, their ideas found refuge in unlikely places: monasteries along the Silk Road, Moorish palaces in Spain, the memory of scholars who carried fragments across continents. The story of these libraries isn't just about what was lost, it's about what refused to die and the stubborn human belief that light, once kindled, can never fully be extinguished. In the twilight of Alexandria's intellectual golden age, one figure stood apart, not just for her brilliance, but for the sheer improbability of her existence in that time and place. Hypatia, born around the year 350, wasn't merely a scholar in a city of scholars. She was a woman who commanded respect in fields dominated by men, a mathematician who refined the astrolabe into a precision instrument, and a philosopher whose lectures drew students from across the Mediterranean. Picture her walking the library's halls in the traditional philosopher's cloak, discussing geometry with the same authority as her male peers, a sight so extraordinary that even her harshest critics couldn't ignore her genius. Her contributions to measurement were both practical and profound. Building on Ptolemy's star charts, she improved the plane astrolabe, a handheld device that mapped celestial movements onto adjustable metal plates. This wasn't just an upgrade, it transformed how sailors and astronomers calculated time, latitude, and planetary positions. Imagine a tool so versatile it could predict sunrise in Athens while simultaneously solving geometric problems in Alexandria. Hypatia's refinements made these calculations accessible, turning the astrolabe from a specialist's instrument into a cornerstone of navigation and astronomy for centuries. Yet her true legacy lay in the classroom. At a time when most women were excluded from formal education, Hypatia led public lectures on Euclid's geometry and Diophantus' algebra, subjects considered the pinnacle of intellectual achievement. Her students, both Christian and pagan, later wrote of her ability to distill complex theories into clear, logical steps. One of them, Synesius of Cyrene, credited her with designing a hydrometer to measure liquid density, a device that blended physics, mathematics, and engineering. This interdisciplinary approach was her trademark. She didn't just teach knowledge, she showed how it interconnected. The motion of planets linked to the angles of triangles, the flow of water tied to numerical ratios. But Hypatia's story carries a shadow. As religious tensions engulfed Alexandria, her status as a pagan intellectual made her a target. In 415, a mob of Christian zealots dragged her from her chariot, murdering her in a brutal act that shocked the empire. The tragedy wasn't just the loss of a life, it was the silencing of a mind that had pushed the boundaries of what measurement could achieve. Her death marked more than the end of a scholar. It signaled the closing of an era where reason and inquiry had flourished in Alexandria's streets. What survives, though, is the echo of her influence. The astrolabe designs she perfected became the foundation for Islamic astronomers like Al-Khwarizmi, who further refined them during the golden age of Islam. The commentaries she wrote on classical texts, though lost to time, were quoted by medieval scholars who preserved fragments of her insights. Most importantly, she left a template for what a scholar could be, relentless in pursuit of truth, unbound by the expectations of her gender, and fearless in the face of a world that wasn't ready for her. In an age that measured the heavens but often forgot to measure its own prejudices, Hypatia's life was a reminder that progress isn't just about tools and numbers, it's about who gets to hold them. The Silk Road wasn't just a highway for silks and spices, it was a living network where ideas flowed as freely as goods, connecting distant minds in a shared pursuit of knowledge. Picture a caravan winding through the Pamir Mountains, its bundles hiding not just precious cargo but scrolls of Greek geometry, Indian astronomical tables, and Chinese star maps, all jostling together in the same saddlebags. This was how measurement techniques traveled, not in deliberate missions of scholarship, but in the quiet exchanges between traders, pilgrims, and diplomats who carried fragments of wisdom across continents. In the bustling markets of Samarkand or Chang'an, a Persian merchant might barter not only for porcelain, but for a new way to calculate the angle of a shadow, while a Chinese official could adopt Babylonian water clocks to refine his own celestial observations. The fusion of Greek and Indian mathematics stands as one of the most transformative collisions of ideas. When Alexander's armies reached the Indus Valley, they left behind more than ruins. They planted the seeds of Euclidean geometry, which later blossomed in the works of scholars like Aryabhata. This 5th-century Indian mathematician didn't just absorb Greek theories, he reinvented them, calculating pi to 4 decimal places and proposing a heliocentric model centuries before Copernicus. Meanwhile, Chinese astronomers who had long tracked comets with meticulous records encountered Greek celestial spheres and adapted them into their own cosmological frameworks. The result, star charts that blended the precision of Hipparchus with the practical artistry of Han Dynasty instrument makers. Perhaps no invention better symbolizes this cross-pollination than the armillary sphere. Originally a Greek tool for modeling planetary motion, it evolved as it traveled eastward. Chinese astronomers added rings to represent their own celestial equator, while Persian scholars engraved theirs with Arabic calligraphy. By the time these devices reached Renaissance Europe, they bore the fingerprints of a dozen cultures, each layer of innovation making the instrument more versatile. Even the humble abacus, often associated solely with China, owes its spread to Silk Road merchants who recognized its power to simplify calculations across languages and currencies. What's often overlooked is how these exchanges relied on mutual respect rather than domination. When the Tang dynasty established its astronomical bureau, it welcomed Syriac Nestorian Christians, Indian monks, and Zoroastrian astrologers as equal contributors. In Baghdad's House of Wisdom, scholars translated Ptolemy's Almagest into Arabic not to supplant local knowledge but to enrich it, a collaborative spirit that produced breakthroughs like Al-Khwarizmi's systematic algebra. This wasn't just borrowing, it was a dialogue where each culture asked, "How can we make this better?" The legacy of this collaboration echoes in tools we still use today. The sexagesimal system, born in Babylon and refined by Greeks, became the foundation for measuring time and angles, yet it reached Europe via Arabic intermediaries who added the game-changing concept of zero from Indian mathematics. Even the Astrolabe, Hypatia's masterpiece, gained its iconic form through Islamic artisans who scaled it down for portability and added prayer time indicators. These weren't mere tweaks, they were reinventions, proving that the most enduring advances arise when diverse minds tackle the same problem. As we turn eastward, the contributions of Chinese scholars like Zhang Heng demand recognition. In the 2nd century, his seismoscope, a bronze vessel adorned with dragons and toads, could detect earthquakes hundreds of miles away, its precision unmatched until modern times. His celestial globe, powered by water wheels, mirrored the heavens' motion with an accuracy that wouldn't be rivaled in Europe for over a millennium. These weren't isolated triumphs but part of a continuum, where the Silk Road's intellectual traffic ensured that every breakthrough, whether from Alexandria or Luoyang, became part of humanity's shared inheritance. While Greek astronomers mapped the heavens with geometry, ancient China charted the cosmos with a precision born from relentless record-keeping. Imagine imperial scribes in the Han Dynasty, perched on observatory platforms night after night, inscribing every celestial event onto bamboo slips, not just stars and planets, but the sudden appearance of guest stars we now call supernova, the ghostly sweep of comets, even the precise timing of solar eclipses down to the quarter hour. These weren't mere observations, they were a sacred duty, rooted in the belief that the heavens mirrored earthly affairs. When a comet streaked across the sky in 166, court astrologers interpreted it as a portent, yet they also logged its path with such accuracy that modern astronomers can still reconstruct its orbit. At the heart of this system stood instruments of breathtaking sophistication. The armillary sphere, known in China as the Hanyi, evolved into a masterpiece of bronze rings and sighting tubes, its design refined by generations of scholars. Zhang Heng's 2nd century version didn't just model the sky, it rotated via water power, simulating celestial motion in real time. But the real marvel was how these tools served dual purposes. The same eclipse prediction that guided agricultural calendars also determined whether the emperor should perform rituals to appease cosmic imbalances. Astronomy and astrology weren't at odds, they were two sides of the same bronze mirror. What set China apart was its bureaucratic rigor. While Ptolemy worked alone in Alexandria, Chinese astronomy was a state-sponsored enterprise. The Astronomical Bureau, established as early as the Zhou dynasty, maintained continuous records for over 2,000 years. Their star catalogues, like the one compiled by Shi Shen in the 4th century BCE, listed 120 constellations and 800 stars with precise coordinates. When a solar eclipse occurred in 1360 BCE, later scribes could cross-reference it with earlier accounts, building a timeline of celestial cycles that stretched back centuries. This institutional memory allowed them to spot patterns invisible to isolated scholars like the 11-year sunspot cycle, noted in hand texts 18 centuries before Galileo. Their predictive methods revealed a unique blend of math and metaphysics. Unlike Greeks relying on geometric models, Chinese astronomers used periodicity, the idea that celestial events repeat in fixed intervals. By analyzing past eclipses, they derived the triple conjunction cycle of 23,390 months, enabling forecasts with 90% accuracy. Comets, often feared as omens, were meticulously tracked to demystify them. Records from the Warring States period describe Halley's Comet's appearances with such detail that modern scientists still cite them. Even the layout of capitals mirrored cosmic order. Chang'an streets aligned with cardinal directions, while the Ming dynasty's Beijing Observatory faced southward, reflecting the emperor's symbolic connection to the pole star. As we turn toward the Indian subcontinent, another astronomical tradition emerges, one where mathematics married mythology. Aryabhata's 5th century calculations proposed elliptical orbits and a spinning Earth, while Brahmagupta's Brahmasputa Siddhanta laid the groundwork for algebraic astronomy. But what unified these diverse cultures was a shared conviction. The cosmos wasn't just to be observed, but measured, decoded, and ultimately understood as a grand, interconnected system. Whether through Chinese bureaucracy or Indian calculus, the message was clear: the sky's mysteries yield not to magic, but to method. 1,000 years before Copernicus gazed at the stars, a young Indian scholar named Aryabhata sat beneath the monsoon skies of Pataliputra, scribbling revelations that would shake humanity's understanding of the cosmos. Born in 476, at the height of India's Gupta Empire, Aryabhata wasn't just a mathematician, he was a revolutionary who saw numbers as the key to unlocking the universe's deepest patterns. His magnum opus, the Aryabhata, distilled a lifetime of celestial calculations into poetic verses, blending rigorous trigonometry with bold cosmological claims. Among them, a startling suggestion that the Earth spins on its axis, creating the illusion of a moving sky, an idea so radical it wouldn't gain acceptance for another millennium. Central to his work was an obsession with precision. While Greek mathematicians like Archimedes had approximated pi as 22/7, Aryabhata pushed further, calculating it to 4 decimal places, 3.1416, a value so accurate it remained unmatched in his era. But his genius didn't stop there. He devised a unique system of trigonometry using versines, a function similar to modern sine, to chart planetary motion, creating tables that predicted eclipses and tracked the moon's wobble with eerie accuracy. Picture this: without telescopes or calculus, he deduced the moon's reflected light by comparing its brightness during different phases, then used geometry to estimate its distance from Earth. These weren't just abstract exercises, they were the foundation for India's lunar calendars and navigational tools still used by sailors centuries later. What's often overlooked is how Aryabhata's ideas bridged cultural divides. His trigonometric methods, later refined by scholars like Brahmagupta, mirrored Greek advancements while introducing innovations like the concept of zero as a placeholder. When Islamic scholars encountered these texts during the Abbasid Caliphate, they recognized a kindred spirit in Aryabhata's blend of computation and observation. Figures like Al-Khwarizmi adapted his sign tables, while Persian astronomers cited his eclipse predictions in their own star catalogues. This wasn't mere coincidence, it was intellectual synergy, proving that mathematics, like the monsoons, knows no borders. As the Gupta Empire faded, Aryabhata's legacy didn't dim, it migrated. Through Sanskrit texts carried along trade routes, his ideas reached Baghdad's House of Wisdom, where they mingled with Ptolemy's geometric models and Babylonian arithmetic. The result, a mathematical renaissance that would fuel the Islamic Golden Age, where scholars didn't just preserve ancient knowledge but expanded it into new frontiers of algebra and astronomy. Aryabhata's spinning Earth, once dismissed as heresy, became a whisper in the ear of later thinkers daring to reimagine the cosmos. His story reminds us that revolutions often begin not with shouts, but with numbers scratched onto palm leaves, waiting for the world to catch up. While Europe navigated the early Middle Ages, a Persian polymath named Al-Biruni was rewriting the rules of celestial measurement with nothing but trigonometry and relentless curiosity. Picture this 11th century Afghanistan, where Al-Biruni perched atop a mountain near the Indus Valley, staring at the horizon with an instrument of his own design. His goal, to calculate the Earth's radius with unprecedented precision, not by repeating Eratosthenes' shadow method, but by crafting an entirely new approach. What unfolded was a masterclass in ingenuity. His breakthrough came from a simple yet profound observation. The angle at which the horizon dips below eye level changes with altitude. By measuring this dip from a known height, like standing atop a mountain, he could use trigonometry to derive the Earth's curvature. Here's how it worked. First, he calculated the mountain's height using a clever combination of astrolabe readings and geometric triangulation. Then, he measured the angle between the horizontal plane and the visible horizon from the summit. The steeper the dip, the smaller the Earth's radius. His calculations yielded a value of 6,339 kilometers, just 66 kilometers shy of today's accepted figure. For context, that's like measuring the distance from New York to Boston and being off by less than a mile. But Al-Biruni's genius didn't stop there. He realized earlier attempts failed because they didn't account for atmospheric refraction, the way Earth's atmosphere bends light, distorting observations. By factoring this into his equations, he achieved a level of accuracy that wouldn't be rivaled for centuries. His meticulousness extended to geography too. He compiled latitude and longitude data for hundreds of cities, correcting errors in Ptolemy's maps and even estimating the Earth's axial tilt to within minutes of the true value. The tools behind these feats were as innovative as the methods. Al-Biruni's quadrant, a brass masterpiece etched with precise degree markings, allowed him to measure star positions to fractions of a degree. His cylindrical astrolabe, a portable marvel, could determine time, latitude, and prayer direction with a single alignment. These weren't just instruments, they were extensions of his mind, designed to squeeze every ounce of precision from naked eye astronomy. What's often overlooked is how Al-Biruni bridged disciplines. His work fused Hindu, Greek, and Islamic astronomy into a cohesive system, proving that scientific progress thrives on cultural exchange. When he calculated the Earth's circumference, he didn't just cite Greek texts, he referenced Sanskrit manuscripts and debated Indian scholars, blending their insights with his own. His legacy reminds us that the greatest measurements aren't just about numbers, they're about the willingness to stand on the shoulders of every available giant, no matter where they're from. As the Islamic Golden Age flourished, tools like his quadrant spread from Baghdad to Cordoba, turning observatories into powerhouses of discovery. The same instruments that measured the Earth's curve would later guide navigators across oceans, proving once again that when curiosity is paired with precision, even the sky isn't the limit. The astrolabe wasn't just a tool, it was a medieval masterpiece of brass and mathematics, a handheld universe that fit in the palm of a scholar's hand. Picture a disk the size of a dinner plate, its surface etched with concentric circles, zodiac signs, and intricate scales, all rotating around a central pin. By aligning its movable parts with the sun or a known star, a user could solve problems that would stump modern calculators, telling time at any hour, predicting sunrise, even determining the height of a distant minaret. This wasn't just an instrument, it was the closest thing the ancient world had to a smartphone, compressing the cosmos into a portable, multifunctional device. At its core, the astrolabe worked by projecting the three-dimensional sky onto a two-dimensional plate, a concept borrowed from Greek geometry but perfected by Islamic scholars. The reter, a pierced metal web atop the disk, represented fixed stars, while the tympan beneath it held latitude-specific markings. Rotate the reter to match a star's position, and suddenly, the device became a celestial calculator. Need to know when twilight would end in Cordoba during Ramadan? Align the rule with Vega's position, and the answer appeared where the markings intersected. Farmers used it to plan planting, architects to align mosques with Mecca, poets even wove its symmetry into verses about love and destiny. What's often forgotten is how the astrolabe blurred the line between science and art. Persian craftsmen adorned theirs with floral arabesques and Quranic verses, turning each instrument into a fusion of devotion and precision. In Constantinople, Byzantine makers inlaid them with silver and lapis lazuli, while European versions featured saints and zodiac beasts. These weren't mere decorations, they reflected a worldview where beauty and accuracy were inseparable. The astrolabe's elegance wasn't incidental, it was proof that understanding the heavens required both logic and wonder. By the 12th century, this Islamic innovation had crossed into Europe via translations in Toledo and Sicily, where scholars like Chaucer, yes, the Canterbury Tales poet, wrote instruction manuals for its use. Suddenly, monks who'd never left their cloisters could measure the universe, and sailors could venture beyond sight of shore with newfound confidence. The astrolabe became a badge of learning, so coveted that universities required students to master its use before earning degrees. It wasn't just a tool, it was a passport to the intellectual elite. Yet its golden age couldn't last forever. As the Renaissance dawned, newer instruments like the quadrant and sextant began to eclipse it. But here's the twist, the astrolabe's decline wasn't the end of its story, it was a rebirth. Scholars rediscovering ancient texts realized this device held echoes of Ptolemy's geometry and Hypatia's refinements. In tracing its origins, they uncovered a forgotten truth, that the wisdom of antiquity hadn't vanished. It had traveled, evolved, and waited for the right moment to spark a revolution. The astrolabe, once a bridge between cultures, became a bridge across time, connecting the Renaissance not just to the Islamic Golden Age, but to the very roots of Greek and Indian astronomy. And in that rediscovery lay a revelation. Progress isn't a straight line, but a great circle, forever returning to the insights of those who first dared to measure the sky. The Renaissance didn't just rediscover ancient knowledge, it set it ablaze with new purpose. Picture Nicolaus Copernicus, hunched over a manuscript in a Polish cathedral tower, scribbling notes in the margins of Ptolemy's Almagest. The same text that had cemented Earth as the universe's center for 14 centuries now whispered a different truth to him, a truth buried in the geometry of planetary motion. What Copernicus saw wasn't just flawed math, it was a key, By shifting the sun to the center of his model, those stubborn planetary loops that had forced Ptolemy to add endless epicycles suddenly smoothed into elegant ellipses. The universe hadn't changed, just humanity's courage to interpret it. Yet this revolution wasn't born from theory alone. It took sharper eyes and finer tools to crack the celestial code. When Galileo turned his improved telescope toward Jupiter in 1610, he didn't just see moons orbiting another world. He saw living proof that not everything circled Earth. His sketches of Venus's phases, waxing and waning like a miniature moon, shattered the old geocentric dogma. But here's what's often overlooked. Galileo's triumph owed as much to ancient methods as to his lenses. The precise angular measurements he made relied on techniques refined by Hipparchus 2,000 years earlier. Even his famous discovery of sunspots, blemishes on the supposedly perfect sun, echoed Chinese astronomers who'd recorded them centuries before telescopes existed. The real drama of this era wasn't just in the stars, but in the clash between tradition and evidence. When Jesuit astronomers in Rome confirmed Galileo's findings with their own observations, they faced a painful choice: reject the Church's Aristotelian teachings or deny what their instruments revealed. Some chose compromise, like Christopher Clavius, who adjusted the Gregorian calendar using Copernican calculations while publicly dismissing heliocentrism. Others, like Giordano Bruno, paid with their lives for insisting on an infinite universe filled with worlds, an idea straight from Democritus' ancient speculations. This tension between old and new wasn't mere stubbornness. It was the growing pains of a civilization learning to trust measurement over myth. What sealed the heliocentric model's victory wasn't rhetoric but precision. Johannes Kepler, poring over Tycho Brahe's lifetime of naked eye observations, found Mars' orbit fit not a perfect circle but an ellipse, a shape Greek geometry had described but never dared apply to the heavens. His laws of planetary motion, published in 1609, didn't just correct Copernicus, they vindicated Aristarchus' ancient intuition that mathematics governed cosmic order. The same geometric tools Euclid had sharpened now carved a path to Newton's gravity, proving that ancient and modern science weren't rivals but chapters in one unfolding story. The Renaissance's true gift was this: it taught us that progress doesn't abandon the past, it redeems it. When Galileo defended heliocentrism by citing Archimedes' lever, "Give me a place to stand, and I shall move the earth," he wasn't just quoting an old physicist. He was claiming his place in a lineage of thinkers who dared to measure what others called divine. The telescopes and quadrants of this era didn't replace the astrolabe, they fulfilled its promise, turning speculative models into measurable reality. And in that transformation lay a lesson for every age. The answers we seek are often hidden in plain sight, waiting for the right tools and the right minds to bring them into focus. The echoes of ancient measurement techniques resonate in ways those early scholars could never have imagined. Every time your smartphone's GPS pinpoints your location within feet, it relies on principles first explored by Eratosthenes' triangulation and the geometry of spheres. Modern satellites may circle the Earth instead of measuring shadows at noon, but the foundational idea remains the same. The universe operates by rules we can decode through mathematics. Even space exploration carries this legacy forward. When NASA Voyager probes charted their course past Jupiter and Saturn, their trajectories were calculated using the same trigonometric methods Hipparchus employed to map the stars, refined over millennia but rooted in ancient genius. Consider the humble sextant, still carried as a backup on ships despite our digital age. Its design traces back to the astrolabes of Islamic astronomers and the quadrants of Greek observers, proving that some tools transcend time because they embody timeless truths. The James Webb Space Telescope, peering back to the dawn of galaxies, aligns its mirrors using algorithms derived from Ptolemy's star charts, correcting for distortions in a way that would make ancient sky watchers nod in recognition. What these connections reveal isn't just continuity, but a shared language of curiosity that spans civilizations. Yet the true legacy isn't just in tools or equations. It's in the mindset those early thinkers modeled the audacity to believe the unknown could be measured. When the Babylonians tracked Venus cycles or the Maya predicted eclipses, they weren't just collecting data, they were asserting that the cosmos followed patterns waiting to be uncovered. This conviction fuels modern science, from quantum physicists measuring particles we can't see to epidemiologists modeling invisible viral spread. The methods have grown sophisticated, but the impulse remains unchanged to impose order on chaos through observation and numbers. Beneath these achievements lies a deeper philosophical thread. Ancient measurements weren't just about utility, they were acts of meaning-making. The Chinese astronomer who recorded a supernova wasn't merely logging an event, he was anchoring human experience within a vast, measurable cosmos. The Greek geometers proving the Earth's curvature weren't just solving puzzles, they were declaring that reality, no matter how immense, could be comprehended. In an age where we grapple with climate change and deep space mysteries, their legacy reminds us that measurement is more than calculation. It's the first step toward understanding our place in something far greater. Perhaps that's why these ancient techniques endure. They represent more than historical footnotes. They're testaments to humanity's restless need to reach beyond the visible. From the first shadow cast by a stick to the laser reflectors left on the moon, every act of measurement is a bridge between what we know and what we yearn to discover. The tools may change, but the quest to quantify, to map, to grasp remains as timeless as the stars themselves. Even the greatest minds of antiquity stumbled in the dark before finding light. For all their brilliance, ancient scholars held beliefs that seem astonishing today, ideas like the Earth resting on a giant turtle's back, or the planets embedded in crystal spheres that chimed as they turned. These weren't failures of intellect, but the inevitable growing pains of a species learning to measure the universe with nothing but naked eyes and raw curiosity. Take the notion of a flat Earth. While Eratosthenes calculated its curvature in the 3rd century BCE, many of his contemporaries, even brilliant thinkers like Thales, imagined our world as a floating disk beneath a domed sky. The irony, their very tools for celestial navigation, like the gnomons' shifting shadows, subtly disproved their own flat Earth assumptions, yet cultural inertia kept the idea alive for centuries. Some misconceptions arose from the limits of observation. Ptolemy's geocentric model, with its labyrinth of epicycles, wasn't willful ignorance, it was the best possible fit for the data available. Without telescopes, planets truly did appear to reverse course in the night sky, and stars showed no detectable parallax to suggest Earth's motion. When observations clashed with theory, scholars adjusted the math rather than abandon cherished axioms, adding layers of complexity to preserve the illusion of cosmic perfection. This wasn't unscientific. It was science in its earliest form, testing, refining, and sometimes clinging to flawed frameworks until better tools arrived. What's remarkable isn't the errors themselves, but how they were challenged. When Aristarchus proposed a heliocentric system in the 3rd century BCE, his ideas were dismissed not just for defying common sense, but for threatening the philosophical order. To suggest Earth wasn't the universe's center required more than math. It demanded the courage to upend humanity's cosmic significance. Similar resistance met Anaxagoras when he claimed the sun was a molten rock, not a god's chariot, or when Hypatia's astronomical teachings challenged religious dogma. Progress often came at personal risk. proving that measurement alone couldn't overthrow tradition. It needed mavericks willing to stake reputations on inconvenient truths. These historical missteps reveal a deeper truth about how knowledge evolves. Ancient astronomers didn't fail, they prototyped. Like a sculptor roughing out a block of marble, they removed the grossest errors so later minds could refine the details. Ptolemy's epicycles, though wrong, honed the mathematics of curves that Kepler would later apply to elliptical orbits. Babylonian eclipse records, despite their supernatural interpretations, provided the data that revealed the Saros cycle, an 18-year pattern still used today. Even flat Earth myths served a purpose. By debating them, scholars sharpened the arguments for a spherical world, turning speculation into testable theory. Modern science hasn't erased these early struggles, it's built upon them. Today's satellites measure Earth's circumference to the millimeter, yet they rely on the same geometric principles Eratosthenes used with sticks and shadows. Our understanding of planetary motion has grown exponentially, but it began with those first painstaking star charts scratched onto clay tablets. The real lesson isn't that the ancients were wrong, but that they dared to be right in increments, each correction a stepping stone across the river of ignorance. Their legacy isn't in the answers they got wrong, but in the questions they taught us to ask, and the humility to remember that even our finest measurements are just shadows of truths waiting to be uncovered. Today's most advanced telescopes and satellites may seem worlds apart from the bronze astrolabes and shadow sticks of antiquity, but strip away the technology, and you'll find the same spark of curiosity driving them. The Hubble Space Telescope, orbiting high above Earth's distorting atmosphere, operates on the same fundamental principle as Ptolemy's star charts, capturing light to map the unseen. Its mirrors, polished to atomic-level precision, are the spiritual descendants of the polished obsidian mirrors Aztec priests used to track Venus. Even the James Webb Telescope's infrared eyes, peering back to the dawn of time, echo the ancient Chinese astronomers who recorded guest stars, supernova visible for months before fading into obscurity. The tools have grown exponentially more powerful, but the mission remains unchanged: to measure what was once thought immeasurable. Consider how modern GPS relies on triangulation, a technique Hipparchus pioneered in the 2nd century BCE when he calculated the distances to stars using parallax. Instead of comparing observations from 2 Greek cities, today's systems use signals from multiple satellites, but the geometric core is identical. Even the atomic clocks aboard those satellites trace their lineage to ancient water clocks and sundials, all seeking to tame time into measurable units. The laser reflectors left on the moon by Apollo astronauts, still used to measure the moon's distance down to the millimeter, are direct heirs to Aristarchus' lunar calculations with Earth's shadow. Progress hasn't replaced these ancient methods, it's amplified them, turning rough estimates into razor-sharp precision. Yet this continuity raises profound questions. The same impulse to measure and map now extends to realms the ancients never imagined, mapping the human genome, predicting climate patterns, even quantifying emotions through biometric data. With such power comes responsibility. Who decides what gets measured and who benefits? The Babylonians tracked stars to serve their kings. Today, satellite data can be wielded for both conservation and surveillance. The ethical lines blur when measurement becomes omnipresent. Just as Tycho Brahe's meticulous star logs were funded by a king seeking astrological advantage, modern research often walks the tightrope between discovery and exploitation. Perhaps the greatest lesson from this unbroken chain of inquiry isn't technical but philosophical. Every leap from sundials to atomic clocks, from armillary spheres to space telescopes, has expanded not just what we know but what we dare to ask. The ancients measured to survive, we measure to transcend. Yet as we stand on the threshold of quantum computing and interstellar probes, their legacy reminds us that tools are only as meaningful as the wisdom with which we use them. The shadow of that first gnomon still stretches across time, challenging us to measure not just the universe, but our place within it. Measurement has never been a neutral act from the moment ancient rulers first counted bushels of grain to tax their subjects. The power to quantify became a tool of control. The same Nile flood records that helped Egyptian farmers plant crops also enabled pharaohs to calculate exact tribute demands. Babylonian merchants didn't just weigh silver for fair trade. They standardized shekel weights stamped with royal seals, turning trust into bureaucracy. Even Eratosthenes' calculation of Earth's circumference served more than curiosity. It gave Alexander's successors the geographic precision to govern their sprawling empire. Knowledge, especially measured knowledge, has always been entwined with power. Consider the Roman census, a marvel of administrative measurement that tracked every citizen's property and status. While it enabled efficient infrastructure like aqueducts and roads, it also cemented social hierarchies. Your measured wealth determined your military obligations and voting rights. Fast forward to the Middle Ages, when Islamic scholars perfected the astrolabe not just for navigation, but to determine prayer times across expanding caliphates, aligning spiritual life with imperial timekeeping. The pattern repeats through history. Precision enables progress but also centralizes authority. The darker chapters reveal how measurement could mask exploitation. Spanish colonists in the Americas twisted indigenous quipu knotted cords used for accounting into tools for extracting silver quotas from enslaved miners. British surveyors in India didn't just map the subcontinent. Their trigonometric surveys facilitated resource extraction, turning sacred rivers into measured irrigation channels for cash crops. Even the kilogram's original definition, a platinum cylinder stored in Paris, echoed colonial dynamics, forcing global trade to bow to European standards. Yet alongside these abuses, measurement has equally been a liberator. When Chinese farmers during the Han Dynasty demanded standardized grain measures to prevent landlord fraud, they weren't rejecting quantification, they were demanding its fair application. The same Islamic astronomers who served caliphs also democratized knowledge, publishing star tables so accurate that any sailor could navigate beyond sight of land. The tension isn't between measuring and not measuring, but between who controls the tools and who benefits. Today's ethical dilemmas magnify these stakes. Satellite imagery tracks deforestation in real time, but also enables corporate land grabs. Algorithms measure human behavior with terrifying precision, promising personalized medicine but risking surveillance capitalism. As we stand on the brink of quantum sensors and AI-driven analytics, the ancient question resurfaces: do we measure to understand or to dominate? The answer lies not in abandoning measurement, but in honoring its original purpose: to illuminate, not manipulate. The future of measurement won't be shaped by technology alone, but by the values we embed in it. Just as the astrolabe once blended science with artistry, tomorrow's tools must balance precision with equity. Perhaps the lesson from those ancient scholars isn't just their methods, but their humility, recognizing that every measurement is a conversation with the unknown, not a conquest of it. As we extend our rulers into quantum realms and distant galaxies, that wisdom may prove our most vital instrument. Imagine Eratosthenes standing before a modern particle accelerator, squinting at the streaks of data revealing dark matter's ghostly influence. Would he reach for his trusty gnomon to measure the immeasurable? The ancients never shied from mysteries, they simply reframed them as problems waiting for the right tools. Dark energy's relentless push against cosmic expansion might have reminded them of Aristotle's horror vacui, the idea that nature abhors emptiness. Ptolemy, faced with quantum entanglement's spooky action at a distance, would likely have devised an elaborate geometric model, threading epicycles through higher dimensions to make the math align. Their genius wasn't in having answers, but in believing every phenomenon, no matter how bizarre, could be quantified through observation and logic. Today's uncharted frontiers would dazzle even the most visionary ancient thinkers. Nanoscale measurement, where atoms are manipulated like celestial bodies, mirrors Archimedes' dream of moving the world with a lever small enough to grasp. The Event Horizon Telescope's planet-sized array capturing a black hole silhouette employs the same triangulation principles Hypatia used to chart stars, just scaled to galactic proportions. Even gravitational wave detectors, sensing ripples in spacetime from colliding neutron stars, echo Zhang Heng's seismoscope, listening to the Earth's whispers. The tools have evolved, but the strategy remains. Translate the invisible into numbers, then let geometry and pattern seeking reveal the rest. What unites these eras is the refusal to accept unknowable as a final answer. The Maya tracked Venus cycles for centuries without telescopes. Modern astronomers hunt exoplanets using the same patience, passing starlight's faint dimming for planetary clues. Al-Biruni's mountaintop calculations of Earth's curvature find their parallel in satellites mapping sea level rise to millimeter precision. Each leap forward rests on the same foundation: curiosity paired with meticulous recording, whether on clay tablets or in cloud servers. The personal lesson here isn't about tools or techniques, but mindset. Ancient scholars thrived on constraints, turning shadows into yardsticks and knotted ropes into calendars. Their legacy challenges us to see measurement not as a technical skill, but as a way of engaging with the world, a reminder that every mystery, from quantum foam to consciousness itself, is just a riddle awaiting the right perspective. The future of discovery belongs to those who, like the ancients, dare to ask how much before declaring how impossible. What made those ancient scholars truly remarkable wasn't just their intellect, it was their stubborn refusal to accept the limits of their time. Picture Eratosthenes waiting year after year for the summer solstice, knowing his calculation of Earth size hinged on a single day's shadow, or Hypatia, refining her astrolabe designs through countless iterations, each adjustment a testament to patience in pursuit of precision. Their greatest tool wasn't geometry or bronze instruments, it was persistence, the willingness to fail and try again in a world without instant answers. This quality transcends eras, reminding us that breakthroughs rarely come from flashes of genius alone, but from the quiet accumulation of observations, the courage to question what everyone knows, and the resilience to keep measuring when the numbers don't yet make sense. Creativity flourished within those constraints. Without satellites, ancient astronomers turned Earth's shadow into a cosmic ruler. Lacking precise clocks, they used water's steady drip to mark the hours. When the Maya needed to predict eclipses across generations, they didn't invent new technology, they stacked cycles of time like nested bowls, finding patterns where others saw chaos. Their ingenuity whispers to us across centuries. Limitations aren't barriers, but invitations to think differently. Today's challenges, from climate modeling to AI ethics, demand this same inventive spirit, blending old wisdom with new tools to solve problems no single discipline can untangle alone. Collaboration was their silent superpower. The accuracy of Ptolemy's star charts relied on Babylonian records centuries older. Chinese eclipse predictions absorbed Greek geometry via Silk Road exchanges. Even rivals like Brahmagupta and Al-Khwarizmi built on each other's math, proving that knowledge grows when shared. This interconnectedness mirrors modern science's best moments, like the global teams behind black hole imaging or mRNA vaccines, where diverse perspectives crack problems no lone genius could. The lesson, curiosity thrives in conversation, whether across Alexandrian lecture halls or digital forums today. At its core, this relentless drive to measure reflects something profoundly human, the need to find order in chaos, to grasp our place in the vast unknown. From the first lunar calendars scratched onto bone to the petabytes of data from the James Webb Telescope, we're still asking the same questions, just with finer tools. That continuity is worth celebrating and continuing. Whether you're tracking fitness metrics, stargazing with an app, or simply marveling at how shadows lengthen with the seasons, you're part of this unbroken chain of inquiry. The ancients didn't just leave us answers, they passed down a mindset. Keep measuring, keep questioning, and above all, keep wondering at the immeasurable, because every generation's impossible eventually becomes someone's breakthrough. To dive deeper, consider exploring reconstructions of ancient instruments like the astrolabe or quadrants. Many museums offer interactive replicas. Or try Eratosthenes' experiment yourself. All you need is a stick and a sunny day. The real magic happens when history's lessons spark your own curiosity. What will you measure next? If this journey through ancient measurement has sparked your curiosity, you're not alone, and the adventure doesn't end here. For hands-on learners, The History and Practice of Ancient Astronomy by James Evans is a treasure trove, blending rigorous scholarship with step-by-step guides to recreating Babylonian eclipse predictions or Greek geometric proofs. Prefer visuals? The BBC Ancient Worlds series brings Alexandria's streets and Mayan observatories to life, while the Cosmos Reboots episode, Sisters of the Sun, pays homage to Hypatia's legacy with stunning animations. Dive deeper with digitized manuscripts like the Dresden Codex, now fully scanned by the Saxon State Library. Its vibrant Venus tables and eclipse glyphs are just a click away. The British Museum's online collection lets you zoom in on cuneiform tablets where Babylonian astronomers logged Jupiter's movements, their wedge-shaped script still sharp after millennia. For something tactile, replica astrolabes from museums like the Museum of the History of Science in Oxford offer a chance to hold the universe in your hands, just as medieval scholars did. If you're craving community, forums like the Ancient World online blog curate open-access journals on everything from Roman surveying tools to Inca quipu knots. Or join citizen science projects like Zooniverse's Ancient Lives, where volunteers transcribe Greek papyri. You might stumble upon a lost star catalogue or merchant's ledger that reshapes our understanding of ancient commerce and cosmology. What makes these resources so powerful isn't just the information they preserve, it's the way they bridge time. Holding a digital facsimile of Ptolemy's Almagest or tracing the lines of an Egyptian sundial connects you directly to minds that grappled with the same skies we see today. Their questions: how far, how vast, how ordered are ours too? That's the real gift of history, not just learning about the past, but finding your place in its unbroken chain of wonder. So grab a compass, open a star map, or simply step outside tonight and look up. The same stars that guided Eratosthenes and Hypatia still shine, inviting you to measure, explore, and imagine. The tools have changed, but the human desire to map the unknown, that's timeless. There's a hauntingly beautiful passage carved into an ancient Egyptian temple, written by a nameless astronomer 3,000 years ago. To measure the heavens is to walk with the gods, yet the more we grasp, the vaster the unknown becomes. That paradox lies at the heart of every great discovery. The deeper we delve, the more we realize how much remains untouched. Think of Eratosthenes standing beneath the noonday sun, his shadow stretching across the sand as he calculated the Earth's curve. In that moment, he didn't just solve a puzzle, he uncovered a dozen new questions waiting in the wings. How high do those heavens stretch? What dances beyond the edge of the visible? The answers he couldn't reach didn't discourage him, they lit the path for those who followed. Consider the words of Hypatia, whispered to her students in Alexandria's lecture halls. Wonder is the compass that points beyond knowledge. She wasn't just teaching mathematics, she was nurturing a way of seeing one where every measurement, no matter how precise, was a stepping stone to greater mysteries. The same stars she plotted with her astrolabe still hang above us, but now we know each pinprick of light is a sun with its own orbiting worlds, some perhaps hosting life we've yet to imagine. The tools have grown sharper, yet the essential thrill remains unchanged. That moment when numbers dissolve into wonder, when a calculation clicks into place and suddenly, the universe feels both nearer and more astonishing than before. This tension between the measurable and the infinite is where science and poetry meet. When Aristarchus dared to suggest the sun was the center of our celestial dance, he wasn't just rearranging planets, he was redefining humanity's place in the cosmos. His model, though forgotten for centuries, carried a truth deeper than accuracy, that the universe refuses to be contained by any single perspective. Even today, as probes venture beyond our solar system and telescopes peer back to the dawn of time, we're still chasing shadows, still piecing together clues left in starlight and spacetime ripples. The real legacy of those ancient scholars isn't in the answers they left behind, but in the questions they taught us to cherish. Every time a modern physicist grapples with dark matter's invisible grip or an oceanographer maps uncharted trenches, they're walking the same path as the Babylonians who tracked Venus cycles or the Maya who calculated eclipses centuries into the future. The units have changed stadia to light years, water clocks to atomic oscillations, but the longing remains, to touch the untouchable, to name the unnamed. So let's end not with a conclusion, but with an invitation. Step outside tonight and look up. Those same stars that guided Ptolemy and Al-Biruni still shine, their distances now quantified yet no less magical. The moon, whose orbit Aristarchus measured with Earth's shadow, still pulls at our tides, a reminder that some forces transcend numbers. The journey of measurement never truly ends, it simply stretches onward, like light from a star that left its source millennia ago, reaching us at last but carrying whispers of realms still beyond our grasp. And that's the most beautiful equation of all. The more we learn, the more wondrous the unknown becomes. Now that we've journeyed through the incredible minds who measured the cosmos with nothing but shadows, sticks, and sheer brilliance, we want to hear from you. Which scholar's story left you in awe? Was it Eratosthenes calculating the Earth's curve with nothing but a well and a shadow? Hypatia refining the astrolabe under the weight of a world that wasn't ready for her genius? Or maybe Al-Biruni standing on that mountain and measuring the horizon's dip like a cosmic detective? Drop your thoughts in the comments. We'd love to know which moment made you see the ancient world in a new light. If these stories of curiosity and perseverance resonated with you, consider hitting that subscribe button. There are so many more historical mysteries waiting to be unraveled. From the lost technologies of Atlantis to the secret codes hidden in medieval manuscripts. Every click takes you deeper into humanity's greatest puzzles, where the past isn't just remembered but relived. And hey, if you've ever tried recreating one of these ancient experiments yourself, tell us how it went. Did you measure a shadow at noon like Eratosthenes? Track the moon's phases like the Babylonians, Whether you're a history buff, a science enthusiast, or just someone who loves a good mystery, you're exactly the kind of thinker these stories were meant for. Let's keep the conversation going, because the best discoveries happen when we explore them together. Don't forget to ring the bell so you won't miss our next adventure into the unknown. Who knows, maybe the next video will feature an idea from these very comments. After all, that's how knowledge grows, one question, one measurement, one shared insight at a time. See you in the next chapter of history's greatest mysteries. From the humble shadow of a stick planted in Egyptian sand to the laser precision of modern satellites, the story of measurement is humanity's oldest epic, a testament to curiosity that refuses to accept unknowable as an answer. Those ancient scholars, armed with nothing but geometry and grit, didn't just map the world, they laid the invisible scaffolding for everything we've built since. Every time your phone pinpoints your location, every rocket that lands on another planet, every prediction of a solar eclipse years in advance, these aren't just triumphs of modern science. They're the echoes of Eratosthenes measuring the Earth with a well, of Hypatia's Astrolabe tracing star paths, of Zhang Heng's seismoscope trembling at distant quakes. What's breathtaking isn't just their accuracy, it's their audacity. Imagine Aristarchus staring at the moon, convinced its distance could be calculated using Earth's shadow during an eclipse, or Al-Biruni standing on a mountain, realizing the horizon's curve held the key to the planet's size. These weren't just calculations, they were acts of faith that the universe obeyed rules we could uncover, one careful observation at a time. That faith lives on today in the scientists parsing data from the James Webb Telescope. Each pixel of deep space light a continuation of the same quest that began with clay tablets and knotted ropes. The real magic lies in how these ancient methods still whisper to us. Modern astronomers use parallax, the same technique Hipparchus employed, to measure star distances, just with telescopes instead of naked eyes. The global positioning system relies on triangulation, a principle Babylonian surveyors used to map fields. Even quantum physics, with its unfathomable particles, follows mathematical laws first sketched in the sand by Greek geometers. The tools have changed, but the song remains the same: measure, question, repeat. So as we close this journey, let's not just admire the past, let's inherit its spirit. The next time you glance at the moon, remember it was ancient minds who first dared to ask, how far? When you check the time on your phone, think of the water clocks and sundials that carved hours from chaos. Their legacy isn't locked in history books. It's alive in every child gazing at the stars, every student solving their first geometry proof, every explorer, whether in a lab or a backyard, who still believes the universe's greatest mysteries are waiting to be measured. The challenge they leave us is simple but profound. Keep looking up, keep questioning, keep marveling, because the shadows we cast today might just be the yardsticks of tomorrow's impossible discoveries. The cosmos still holds endless riddles who's ready to measure them.